So continue with Professor Dobonat Chaba. Our mechanical testing and fractography studies concluded that the interfacial bonding between the matrix and the glass fillers is responsible for this brittle behavior of GICs. Then we went on to carry out neutron experiment at Harvard Science and Innovation Campus, located in Oxfordshire in the UK. You can see this overview of this facility. The synchrotron is around here. This is target station 1, target station 2. And this is the inside large-scale facility. You have an idea of the instruments. And at ICES, every year they have a year review of all the projects. Our project was among a dozen of the highlighted projects of last year's yearbook. And we've already submitted an abstract for this year's yearbook. So they really like our project. They think we're really up on something good. This instrument is called Vesuvio. It's deep inelastic neutron scattering. It's analogous to X-ray Compton neutron Compton scattering. This is the instrument, samples loaded here, and the neutron beam comes in here to hit this sample. High-speed neutron comes in here to hit this sample, and then the neutrons get scattered and detected here. And we know this distance, and we know this distance from a sample to detector. And the final velocity of the scattered neutron is known. From this equation, if we measure the time it takes a neutron to travel from the source to sample and then to detector, this equation, this is related to the energy, initial energy and the final energy. This energy is how much energy is transferred into the sample. And from this energy, we can calculate the momentum transfer, energy transfer. Our results is this plot. It's in the form of Doppler broadened spectrum. This recoil peak. Our sample has polymer and glass. We mix the two components together, and the cement sets. We measured polymer alone. There's no reaction happening inside. So at 3 hours, 8 hours, the overall peak, there's no shift, there's no change, no reaction happening inside. So there's no significant change. So this instrument is very sensitive to the interaction inside the sample. So our results for the cement at 1.5 hours, 5 hours, here we see significant change happening because of the setting of the cement. It's about 10% difference. This is the total peak in the energy domain. What we did was then we did stoichiometric fitting of the overall peak. We know the elements in this sample. We know their atomic number ratio. We use atomic number ratio times each element's neutron scattering cross-section. That's the ratio of the intensity of the scattering from each atom. Using this ratio to fit this overall peak, we get these small peaks from each atom. So that's the Compton's profile of each atom. Then we measure the width, this full width at half maximum. This is related to the kinetic energy distribution in momentum space. Then at each time point, we calculated, this is the kinetic energy values of each element at each time point. This is hour. So this is for aluminum. And the highest kinetic energy is around 6 hours. This is contrary to the common belief. The common belief in the literature is that as GIC sets, around 24 hours, the strength is highest, the toughness is not high, because this, at 24 hours, our results shows 24 hours aluminum bonding is weaker than 6 hours. That's the reason why GIC is brittle. And from our results, we propose that if we arrest the setting at the half point around 10 hours, the material will become tougher and not so brittle. And these are the results from the other atoms. This fulfill our inquiry of the structural role of other elements of this GIC. Our results are plausible because the carbon results, this carbon exhibits just the opposite trend from aluminum, because as aluminum draws electrons from itself, the electrons moved away from carbon, so carbon has just the opposite trend. And we also carried out state-of-the-art DFT calculations. We built this model of this aluminum octahedral structure. This 6 coordinate has very high electron density. That's the bond strength. Although the 5 bonds are very strong, there's this weakest link. You are only as tough as your weakest link. If this weakest bond breaks, the whole structure collapses. That's why 6 coordinate is over chelated. It's very brittle. So we propose to arrest the setting before the material is over chelated. These are the masterminds behind this international transdisciplinary project.